So we're on to question 16, the final question. And you've got this box here, and you've been given the formula for working out that volume, which is 2x times 25 minus 2x times 25 minus x. And handily, we've got these as the dimensions as well. And it says state the domain of v of x which fits a physical scenario. So what it's saying is, what's the minimum value that x could be, because the domain is the x values, and what's the maximum value that x could be. And the constraint really will be that the dimensions really have to be, each dimension has to be bigger than 0. So already with the dimension of x here, we've got our minimum because the height's going to have to be above 0. Here, we've got 50 minus 2x. So that means that x would have to be equal to 25 for this to be, or sorry, less than 25 for this to have any sort of dimension at all. But if I put 25 into here, I'd have 25 minus 50, so that's not right either. So in a way, this is the dimension which is going to control the maximum value of x. So if we have a look at that one, we would go 25 minus 2x is equal to 0. This is the value that it can't be, but it's the first value that it can't be, which means that 2x is equal to 25 and x is equal to 12.5. So I can say, therefore, x must be bigger than 0, because if x were 0, then we would have no height and therefore no volume. And x also has to be less than 12.5, because if x were to be 12.5, then the depth, or whatever you want to call it, this dimension here, would be 0, in which case the volume would be 0, which is effectively impossible. In interval notation, you would write that as x belongs to 0, 12.5. You can see it's only worth 1 mark, so hopefully that's not too much work to figure that out. You wouldn't have to do too many calculations. Part B, draw a sketch of v of x equals 2x times 25 minus blah, 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 on the set of axes below using only the appropriate domain for the scenario. So we know the domain is 0 to 12.5. So what you can do is you can just shade out all of the negative x values. And if we call that 12.5, you can sort of put a dotted line down there as well and shade that out. So you can say this is the only area that we're going to worry about. And because the volume can't be negative, if you wanted to, you could shade that out as well. So that's one way of doing it. The other way is to draw the entire graph and then just circle the bit which is relevant to the domain. Okay, so we've shaded out the bits that we know it can't be, and now we're going to fit that in. And all we're going to do is we're going to go to our calculator, and I might start a new document for this one. And I'm going to create a graph page, and I'm going to type in the v of x formula, which is 2x multiplied by 25 minus 2x multiplied by 25 minus x. So I think I missed a bracket there somewhere. 25 minus 2x, 25 minus x, like so. Okay, so you might have noticed there was an error message that popped up, and that's because sometimes it gets a bit frantic and you need to make sure there's an explicit multiplication between each part, like so. And that should now give me a graph, a very, very squishy graph like this. It's no good for us to be able to do anything with. So we're going to use menu, window, zoom, and we might need to do this a few times to get it right, but it's worth doing. I know that x is sort of like a fairly small number, so I'm going to go to -1 just so there's a little bit of an axis there, and I'm going to go to say 15 because I know the maximum is 12.5. And then for the y minimum maximum, there's no small ones. I'm going to go to -10, and I don't know what the value is going to be, but I might just take, I don't know, I might just go for 50 and see what happens. Okay, so that's nice. It's going up and it's going down, but I've got nowhere near the right volume here. I'm out by a lot, so I'm going to go to menu, window zoom, window settings. I might say, okay, maybe it's 500 I need. No, menu. This is still better than just using these zoom buttons here because you're really controlling the scale of the graph of the x scale and the y scale. Is it 5,000 I need to go to? Oh, that's a bit better. But now I can't quite see my x-axis because I'm in the thousands now. So I might go menu, window zoom, window setting, and make it a minimum of 500 or something like that. It'll just give me a little bit of scale. There we go, beautiful. So minus a half to 12.5. That's the sort of curve. So now we can actually put that curve in. And I'll draw that. So it's kind of a bit slopey up this side, and then it goes down like that between 0 and 12.5. I don't draw any more of the graph because it's not appropriate for the domain. If you want to, you could put a circle here and a circle here to say that it can't be those values, but everything in between. But I don't think you'd I don't think you'd be pinged if you didn't do that. And because it's a sketch, I think the only other relevant point is the x-intercept. Sorry, the maximum, right? So I might go to Analyze Graph and go to Maximum, and then go to the left and right of that maximum there. Up it goes. 5.28 and 3.01 E plus 3, and I'll explain what that means in a little bit of time. I think it's coming up with the next part of the question. That's basically it for the sketching part, using your GDC. Okay, it says calculate the maximum volume at x equals, calculate the maximum volume of the box and for which this value of x occurs. So we can see here that we've got 5.28 as our maximum, and then we've got 3.01 E plus 3. And then what that means is that you move the decimal place 3 times. So you go 1, 2, 3. And that would give you about 3010, but you can actually get a little bit closer than that, I think. It's a bit too approximate. So I'll show you a couple of things. Number one, I'm going to take this, and if you click on that number, you can actually store the variable, and I might call this M for maximum, for the maximum X value. Why not? And if I do the same thing here and go to store, I can call this the maximum Y value. So I might call it V for the maximum volume. I think that'll be okay. Like so. And they've gone bold to say they've now been stored. So if I now go to control, I've been reading off a different screen. There's the question there. Calculate the maximum possible volume of the box. Blah, 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 blah. Okay. So if I now go to control and then add a page and add my calculator, under var, you can see I've got these three things still stored, where F1 was the function and M was the maximum X value. I wouldn't use X because X is used for different things, and V was the maximum volume. So if I just go V and press return, there it is. That's the full decimal number there. So now I can go 3007 from my GDC. I can also go F1 of M and press return, and that gives me the same value. Or if you just wrote down 5.283 and you went F1 of 5.283, it'll give you not exactly the same number, but accurate enough that you can pretty much get the right answer anyway. So all of these three ways you can get your values. So either storing stuff from the graph and then using it, or if you don't want to do that, quickly writing down the number that you worked out off your graph, adding a calculator page, and then going F1 or whatever the function is, F1 of that number, and that'll give you a pretty accurate answer. But you'll note that it's worth 3 marks, so you can't get away with just writing the number down. That'll give you a mark. So you would say something like this: max volume at x equals 5.283. Okay, so you write that down, and then you can write GDC if you like. Okay, but you've actually written it. I didn't write it down in the end. So 5.283, comma, and then 3007 is the number we worked out, really. So max volume at x equals 5.283. Therefore, V of 5 0.283 is equal to 3007.03, i.e. maximum volume equals 3007 litres, and then you're done for that one. Part D. The box was originally constructed by folding the sides of the sheet of cardboard pictured below to make a rectangular box with an open top. Assuming the thickness of the cardboard is negligible. Okay, this bit here is simply saying you don't have to take that into account when considering the maximum volume. The width of the card or the thickness of the cardboard won't affect the volume in any reasonable way. Water minimization is a goal when making cardboard boxes. Percentage wastage is based on the area of the sheet of cardboard that is cut out before the box is made. Find the percentage of the sheet of cardboard that is wasted when x equals 5. Now, unfortunately, that's a lot of text, and I know that for some people, reading through all that text is hard, but this is where what they're trying to do is they're trying to assess whether you can analyze a context and work out what you need to do. The calculations don't have to be that hard. It's about you being able to interpret what is needed. So find the percentage of the sheet of cardboard that is wasted at x equals 5. So here we go. At x equals 5, each corner is 5 squared equals 25 square centimetres. Okay. Therefore, 4 corners equals 100 square centimetres. There we go. There's my one calculation. Secondly, total area is 25 by 50, which is equal to 1,250 square centimetres. Therefore, percentage waste is going to be how much is wasted, 100, over the total amount of cardboard, which is 1250. And that's a calculator operation. So I would go to my calculator and I would go 100 divided by 1250 equals 2/25. I want it as a decimal though, based upon the context based on the context of what we're looking for. So I'll go Control Enter, and that'll give me the approximation, which is 0.08, and that's 8%. I guess the other thing I could have done as well, if I was just thinking straight from here, is I could say, well, 25 times 4 is 100, and 2 times 4 is 8, so it's 8 over 100, or 8%, rather than, having to rely too much on my calculator. But that is basically it for that question.